Today we're going to be teaching you everything you need to know about how to find the area under the curve using a definite integral. Okay, so first you used Riemann sums to approximate the area under the curve using rectangles and such. But now you have evolved to the definite integral, which allows you to get an exact, a precise interpretation of what is the area under the curve. So let's say that I give you f of x equals x squared. Let's say we're trying to find the area under the curve of a parabola, f of x equals x squared, okay? And let's say I was trying to find the area under the curve from, let me make this steeper, x equals 0 here over to x equals 2 right here. So when I'm trying to find that area under the curve, it's the area bounded between x equals 0 and x equals 2 and between my curve and the x-axis. So that's going to be this shaded region right here. Okay? And the way I find that is I set up my definite integral with my lower bound, the lesser x value on the bottom, the higher bound on the top. I put my function here, x squared dx. Okay? So we did a whole video on solving definite integrals, and I'm going to link that in the top right corner of your screen. And I'm going to give us a refresher. I'm going to give us a summary on how to do it right here. But if you are looking for the integration techniques, like how to actually find antiderivatives, I'd go watch that video, and then you're going to come back here to see how we apply it to area under the curve. Okay, so step one, when we are taking our antiderivative, or rather when we're evaluating our definite integral, is to find the antiderivative. Okay? Step one is to find the antiderivative. Okay? In this case, our function f of x equals x squared. When we're finding an antiderivative, we're trying to find a function big F of x, such that if I differentiate big F of x, I'm going to get my original function back, f of x. So my antiderivative is going to be big F of x. So I'm trying to find a function whose derivative is x squared. To do this, we can use the anti-power rule. The anti-power rule is if I have some function x to the n power, its antiderivative is x to the n plus 1 all over n plus 1. Now you can kind of navigate this on your own, okay? If I were to differentiate something to get x squared, it would probably be an x to the third, right? Because if I differentiate x to the third, I get x squared times 3. I get 3x squared, okay? So that's how I get my squared. But, you know, I don't want 3x squared. I want x squared. So I need to add divide by 3 somewhere in my function. So my final antiderivative is going to be x to the third over 3. Because if I differentiate this, my 3 comes down. This becomes a 2. I get 3x squared over 3. These cancel, and I'm left with just my x squared. This is the formalized rule for that. If I have x to the 2 power, that's going to become x to the 2 plus 1, x to the 3, all over 2 plus 1, all over 3. So once I find my antiderivative in this case is x to the third over 3, I'm going to take down my integral, and I'm going to rewrite it. The integral from 0 to 2 of x squared dx is equal to square brackets, my antiderivative, x to the third over 3, evaluated at my bounds. Take my lower bound 0, it goes in the lower right. Take my upper bound 2, it goes in the top right. And now we're done with the calculus. All that's left for me to do is for me to do some algebra. So the next step is we need to evaluate at the bounds. Okay? What that means is I need to take my antiderivative and I need to plug in x equals 2, 2 to the third over 3, and I need to subtract from that my antiderivative evaluated at the lower bound. I plug in x equals 0, 0 to the third, all over 3. And we know this goes to 0, and this is therefore equal to 2 to the third over 3, which is equal to 8 over 3. So this, 8 thirds, this is the area under my curve. This is the area of this shaded region between my curve and my x-axis, okay? Now we're going to cover a little bit of a nuance that introduces a complication with negative area. Okay, and to demonstrate this, let's start with a new function. F of x equals cosine x. This is the new function we're talking about. Let's draw a graph of it. So I've got my cosine x, and my cosine x is going to oscillate up and down like this. So if I were to label my graph, this right here would be pi over 2, this right here would be pi, this right here would be 3 pi over 2, and so on, okay? So let's first evaluate the integral from 0 to pi over 2 of cosine x dx. Okay, how about you take this? You go solve this integral on your own and come back to me so we can work through it together. So remember, step 1 is to find our antiderivative. We remember from the derivatives unit that the derivative of sine x is cosine x. So the antiderivative of cosine x would be sine x. And I'm going to put my lower bound here, my upper bound here, and I'm going to evaluate it at upper bound minus lower bound. So sine of pi over 2, we know that is 1, minus sine of 0, we know that is 0, so this becomes 1 minus 0, which is 1. So this area right here, bounded underneath my curve, is area 1, okay? Now, the way that negative area comes into this is if I were to evaluate the definite integral from pi over 2 to pi, if I were to evaluate this integral right here, this area under the curve, you're going to see that the area between my x-axis and the curve and the function is going to be a negative area, okay? It is a negative area when I evaluate the area under the curve and my curve is beneath the x-axis. So this area right here becomes a negative area, whereas this area is a positive area, okay? I know it doesn't really make sense. Area can only be positive, but here we're just talking about definite integrals. The definite integral on this interval is a negative number, okay? So we interpret this as a negative area. Now what you're going to see is when we're dealing with cosine x, this area right here and this area right here are exactly the same in magnitude. So this is a positive number, this is a negative number, okay? So what you're going to see is if I were to evaluate my definite integral from 0 all the way up to pi, if I were to evaluate the definite integral on this whole interval, I'm going to have a positive area that's exactly the same size as my negative area, and the two should cancel out, which means you should see that my definite integral evaluates to 0. Let's perform just that. We're going to do the integral from 0 to pi of cosine x dx. So we already know what our antiderivative is. It's going to be sine x, and we're going to evaluate that from 0 to pi. So sine of pi minus sine of 0. So if you remember from our unit circle, we're going to remember that sine of pi is 0, and we know that sine of 0 is 0. So that means our final area is 0, just as we predicted. You will probably come across a problem sooner or later that asks you for the total area, or the real area bounded between the curve and the x-axis. You're going to be asked to find the magnitude of the area, which means, translating that into English, the problem wants you to interpret this area as a positive area, and then find the total magnitude of area bounded by your curve, okay? Let's cover how to do that. So I'm going to replace this here to remind us that this is negative. If we just evaluate the definite integral from 0 to pi, you're going to see we get 0. You're going to see we don't actually get the net magnitude bounded. So the first step when we try and approach this is we need to find a way to separate what our positive area is from what our negative area is. So you have a graph right here, and it's a pretty simple function. So you can kind of picture in your head where the positive area is and where the negative area is. But we're going to cover how to do this in the case that it's a weird function, you don't have the graph, you don't know how to think about the graph, okay? Let's say you want to evaluate this function, the area bounded from 0 to pi, okay? So what we're going to do is we're going to take our function cosine x, and we're going to find where it crosses the x-axis. That means we're going to find where cosine x equals 0, okay? Now, since cosine x is a trig function, cosine x equals 0 an infinite number of times for an infinite number of different x's, but we're only looking on the interval 0 to pi. So in that case, cosine x equals 0 only when x equals pi over 2, as you can see by the graph, okay? Now what we have to do is we have to draw a number line, okay? On the number line, on the left of our number line, we draw our lower bound 0. On the right of our number line, we draw our upper bound pi. And in the middle of our number line, we draw where we cross the x-axis. If you cross the x-axis more than once, you're going to draw more than one line. You're going to divide it into thirds instead of halves. So we're going to put where we cross the x-axis, pi over 2. And then we're going to choose any number between 0 and pi over 2, and we're going to plug that into our function, and we're going to see if we're positive on this interval. So pi over 4. Cosine of pi over 4 is rad 2 over 2. That's a positive number, which means on this interval, our function is positive. Let's say I take 3 pi over 4. Cosine of 3 pi over 4 is negative rad 2 over 2. So this is going to be negative. Our function is going to be negative on the interval pi over 2 to pi, okay? Now that we have this information, we know how to separate the positive area and the negative area. And let me teach you how to do that, okay? So what we're going to be doing here is we're going to be breaking up our integral. So first, we're going to evaluate one integral, which is from our lower bound to our point where we cross the x-axis, 0 to pi over 2 of cosine x dx. And you see, we just evaluated that integral over here. We know that this corresponds to this area, which is a positive area. We know that it's positive area because our function is positive. So we know this is a positive area. And then we're going to evaluate the integral from our x point, pi over 2, all the way up to our final endpoint pi of cosine x dx. Okay? Now we know that this, in this definite integral, corresponds to these bounds, corresponds to a negative area under the curve. So I want to make that a positive area under the curve, so I'm going to negate it. The negative of a negative area is a positive area, okay? And then I'm going to add these two together, okay? If I add this positive area and this now newly positive area, I'm going to get the total magnitude of the area, okay? So I'm just going to convert this into a subtraction. And now let's evaluate these. We just evaluated this integral over here. We know this is 1 minus the integral from pi over 2 to pi of cosine x dx. Let's do step 1, find the antiderivative. We know what the antiderivative is. That is going to equal sine x evaluated from pi over 2 all the way up to pi. And this is going to equal 1 minus, big parentheses, sine of pi minus sine of pi over 2. Now, if you remember from the unit circle, sine of pi is 0. Sine of pi over 2 is 1. So this is going to equal 1 minus 0 minus 1. It's going to equal 1 minus negative 1. It's going to equal 1 plus 1. It's going to equal 2. So now this 2 is our magnitude of the area bounded by our curve, okay? Well, basically what we did is we found out where the negative area is. We isolated the definite integral that corresponds to that negative area, and then we just negated it to make it a positive area, okay? All right, if you believe that you have gained something valuable, leave a like. Leave a like. Okay, if you want more extra help, go to meekextrahelp.com or join the Discord server. That's linked down below. Otherwise, have a fantastic day and enjoy life.